Okay. Hello, everyone. I'm Ignacio, and this is joint work with Tamara and Xavier, rival. And, I'm from INRIA in Paris, and Tamara, she works in Sofia, and I work with Xavier in Paris. Okay, so let's go ahead. So the motivation of this work is to talk about software that is confidential information that basically can be attacked by unwanted actors. So this private information is going to actually be working besides public information, and this public information can then generate leaks of this private information. So the property that studies this such interaction is non-interference, and basically our goal now is to improve the state of the art for the automatic verification of this property. So during the talk, basically, I'm going to be building up different semantics. So symbolic execution and dependencies basically are going to be the building tools that we're going to see to get to our result, which is RedSoundRSE. And also I have RedSoundRSE, which is a different semantic of symbolic execution, but because of time, I won't be able to show it to you. But yeah, can be seen in the paper. Okay, so now we have a small program that is asking if I is bigger than prib. Then we do some assignment to I and prib. And the question is then, what is non-interference? How can we define it? So here, basically, we have to assume first the attacker model, which is basically that the attacker can observe public variables at the beginning and the end of the execution. In this case, we have only I as a public variable, and then we're going to assume that prib is a private variable. And in all the programs that we see, basically, prib is going to be the only confidential variable. And then basically, a program is going to be non-interferent if the private information is not affecting public information in the program. So this is a very high-level introduction, but then we're going to be a bit more in depth. So, and then also, just as a heads up, I'm going to be referring to public information or variables as low variables, meaning low confidentiality, and private variables, we're going to call them high variables. Okay, so then the thing is that this program is actually not non-interferent. So because the value of I actually depends on the value of prib. If the difference between I and prib is big, then the final value of I is going to be affected. And basically, we can see this by just giving a counterexample. So we give two memories where the value of I is the same and the value of prib is different, but then in the final memories, we can see that I is now 2 in the first one and 3 in the second one. So indeed, the value of prib is modifying the value of I in the end. And we can actually characterize these memories basically by saying the set of all pairs of memories, mu1, mu2, where we share the value of I, but then the value of prib must be different, and the value of P must be bigger than the value of I in one of these memories. And this is basically interesting to say that we can characterize a set of memories that can show us that non-interference is not met in this case. And then we have to ask ourselves basically what's going to happen if we use these automatic techniques that we have available. So first, we're just going to define what is being sound incomplete. So we would like our analyzer to be sound incomplete. So for any program P, then we're going to have some analysis P, which is the one that we might be interested in. It's going to tell us whether program P is satisfying non-interference or not. So analysis is going to return either true or false. True meaning that it believes that the program is indeed non-interferent, and false in the other case. So then analysis basically would be sound if we get that when we get the true response, then it implies that the program P is indeed non-interferent. Meanwhile, completeness, or the complete analysis, basically is telling us that if a program P is not non-interferent, then we're going to get that the analysis is going to return false. And basically the two techniques that we want to see today, but first basically we know that this is not possible and there are results showing this. But the two tools that we want to see today, basically dependencies, which is a technique based on abstract interpretation, and that is sound. And then we also want to talk about relational symbolic execution, which is usually complete, can be made sound, and we're going to do it, but usually we assume that it's not sound, just complete. And yeah, and dependencies analysis, basically because it is sound, will not give us a false positive. Meanwhile, the relational symbolic execution analysis will not give us a false negative. And actually, because symbolic execution is based on SMT solvers, the idea is that being complete, it can give us counterexamples. So it can give us actual memories that we can execute to see the problem happening, like to see the violation of a property. Okay, so now we switch programs. We have a different program where I has to be smaller than set, and then we add 1 to I and 5 to prib. So the question again is this program non-interferent? And the answer basically is yes, just because I is depending on the value of set, but there is no relation between I and the value of prib. And again, we can just give some memories, like a pair of memories that basically show us that if we have the same value in I and set, doesn't matter the value of prib, we're going to get the same value for I and set in the end of the execution. And basically, now we'll refer to this as low equality. So we're going to say that mu0 is low equal to mu1. So in the polyvariables I and set, we can see that they share the same values. So basically, we want to see that if in the beginning of the execution, they're low equal, then in the end of the execution, they must be low equal. And we can actually characterize non-interference in this way by basically saying that for every pair of low equal memories, by executing,
You cannot get soundness, completeness, and termination. Is it because the non-interference is undecidable? This dependency analysis obviously is decidable, right? But are you saying that in general the non-interference property is undecidable, right? Maybe.
Yeah. So the thing is that, I mean, in a kind of way, what we can say is that, yeah. So I think that the way to think about it, like a more high level, is that basically to have a complete and sound, it would mean that we can see exactly like a perfect abstraction of the whole semantics of the program. Basically meaning that we don't have no over approximations and no under approximations in the analysis. Yeah. And basically, well, yeah, this is not possible. And
I know you program verification in general is not possible.
Yeah.
Non-interference is also.
Yeah. So basically, the theorem that talks about this states that for non-trivial properties, this is not possible. And definitely, non-interference is not one of those. Yeah. Yeah. Sorry.
You say here will not give false positive. This is abstract interpretation, but abstract interpretation is typically a no false negative.
No, sorry?
No false negative analysis, right?
Well, sorry, maybe a mix-up. Let me see. So what I, besides from what I
complete.
But the idea is that we're going to get this over-approximation of the states. Right. So
you have false positive but no false negative.
Okay, yes. Sorry. Okay, so back to this. Okay, and basically, I was talking about the way we can characterize non-interference is by saying that for every pair of low equal memories, then executing the program should provide us low equal memories again. And then if we have this for every pair, then the program should be non-interferent. Okay, so then the question that we want to ask is that whether can relational symbolic execution analyze such a program? And the answer for now, basically, is no, because then we don't know the value of I and set, so then technically speaking, we can enroll an infinite amount of times, and we don't know when to stop. Meanwhile, the good thing about dependencies is that we will use this program later in the presentation, and dependencies can actually safely tell us that the program is non-interferent, because it doesn't need to enroll the full loop. It's just going to over-approximate its semantics and reach a safe answer. So basically, the goal of the talk is to, well, we have this question. Can we have a relational symbolic execution that is sound, but also is using dependencies when needed to get a better over approximation that is going to allow us to determine if a program is non-interferent or not. And the answer is yes. And this is what we propose. We call it, for now, RedSoundRSE. And basically, it's a combination between relations of execution and dependencies, where we use dependencies to give sound over approximation of loops. Okay. So now we're going to focus on what symbolic execution is first, just to have a knowledge of all the tools that we're going to use. So symbolic execution can be used for non-interference, but the thing is that for this we need to make it relational. So for now I'm just going to introduce the concept of what symbolic execution is, and then we're going to lift this to get an idea of how we can do relational. So the first idea is that in symbolic execution we want to map variables. Instead of concrete values, we want to have them as symbolic expressions. So also during the talk, every time we use this special font, so I map to special I is going to be in this symbolic expression. So we replaced basically the value of 0 for I, and now I can basically represent any number. And the idea is that now this is actually not enough for us to define a symbolic state. What we need is to also add symbolic path, is going to be called, which allows us to handle conditional statements. So now I have just, this is just to give intuition, but it is that we start executing with this state that has the true symbolic path, meaning that it has no constraints over the symbolic store. And then we can then choose to branch on the false branch, so we skip the whole while statement. And this gives us a constraint we can then hook up, and it's going to constrain the whole state. Then we can also go through the true branch and basically having the opposite constraint, telling us that I must be less than 0, than set. And then we can apply the assignment, and this is very nice. Thing is that we can continue executing like this, but this can be infinite. As we said before, we don't know the value of I and set. So yeah, we can execute infinitely. So the thing is that we do want to have an approximation at some point, so that we can soundly take the semantics of the program and then decide whether the program is non-interferent or not. So yeah, so for basically now to be able to talk about this approximation, first we need to see how we can define a relational symbolic execution, and then over that we can build our approximation. So the idea is that we need to lift the symbolic execution to be relational, and this can be done. I mean, the most simple way maybe would be to have two symbolic stores, and then on the symbolic path we can just connect them by saying that the value of I0 must be equal to the value of I1, and set 0 to set 1. But, well, this is actually not so good. So the other option that we can use, well, and this is not good also because we're expanding the symbolic, the symbolic path, which then is going to be more queries to the SMT solver. So we want to avoid this. And, well, actually, also it's not nice to look at. So basically what we can use is this kind of faceted values, which allows us to write in a very more compact way. So basically now we can just combine them into a single symbolic store that has these faceted values. So for I and set, we just put one value, and this is basically going to tell us that I and set are low confidentiality in the program, and P is of high confidentiality. And we have an empty symbolic path, so we made it simpler. And then basically this is all we need for now to think. So now we just want to go to the sound relational symbolic execution. So we can do here an over approximation of this. So we can do the small box, and basically our goal here now is to reach a new state that is going to contain all the states in the box. So a sound over approximation. So basically this I'll do just step by step. But the idea is that first we can copy the state that we had previously. And then, well, this is very simple actually. We just can calculate the set of modifiable variables in the loop. So in this case it would be I and P because they're being assigned. Then we can get new symbolic variables, and this is where we can use the faceted values. So because we have no information about I and P, we just know that they might have been modified. We just assign pairs of values. So this, you can obviously see that this is a very bad choice, because then even if I does not depend on priv and is only being added by 1, we basically are saying that we don't have no information available about I. So we have to put 2 values, meaning that in the 2 executions that we're trying to abstract, we're allowing them to have different value for I. And basically now we just negate the guard of the loop, and actually this is a sound over approximation, but as I said before, it's very bad. So the thing is that now to make this over approximation better, the idea is to use dependencies. So let's see what dependencies are like. And yeah, we have already seen that the relational symbolic execution can be used for non-interference. And dependencies is a different technique based on after interpretation. And actually, instead of expressing values of variables, it expresses their confidentiality level. So it expresses the flow information during the execution of a program. So basically, now we have a smaller program that is very simple, that always assigns a 5 to y, depending on the value of priv. But the thing is that basically this example is going to be good just to see that dependencies can also be very imprecise because they don't handle values. So the idea is that first we have to define security lattice, low and high. Basically, low is going to be the bottom of the lattice. And then we can write dependency state, which is basically going to be a map for variables to the security lattice. So values of the security lattice. And then I skipped basically the semantics of dependencies. But the idea here is that dependencies is picking up that the branch is depending on priv, which has a high security, and then it's going to make any assignment inside this code to go to high. So basically, you're losing information about y. And as I said before, this is because we cannot capture that value of I is 5. We just capture that it depends on the high value. Okay, and next, by assuming that we understand dependencies, and we have already an idea of what relational symbolic execution is, now we can try to make RedSoundRSE, which is our actual contribution to this. So SoundNRSE, the one that we showed before, is sound, but this over approximation is very imprecise. So dependencies are very efficient and basically can give us loop invariants about this flow information. So it's very useful actually. And how can we use dependencies in the relational symbolic execution? So we go back to the program that we had before, which we saw dependencies can safely see whatever is going to happen to the value of I, but relational symbolic execution is going to make a very bad over approximation of I. So the idea, now we're going to go again basically step by step on what the semantic rule of this RedSoundRSE is going to do. So first it copies the value of our symbolic state. Now, before we're basically just getting the modifiable variables or the modified variables. But now, basically what we have to do is that we have our dependency state D, which is going to be generated by having this translation function, which takes our symbolic state. And basically, this is the nice part of having this faceted representation of symbolic values, where as we can see, I is only mapped to one symbolic value. For example, P is mapped to 2 symbolic variables. So basically what this means is that the translation function is just checking whether we have one value or a pair of values. So if we have only one value, then we can map to low, and for P we must map to high, so this is very easy. Then this is where we use the dependency semantics. Basically, we can execute the loop. And actually, because as we said before, the value of I does not depend on set, D prime, so the new state of executing D with the loop, is going to be actually the same as D. And then we can actually get the projection of which variables are mapped to low. So this is going to be I in set. And now again, we do get back to the previous course, which is getting the modifiable variables of the program. And now we can, again, get the new symbolic variables to replace. But now, because we just saw that in the d prime, the dependency state that we got, we can see that I is mapped to low. Basically, it's going to tell us, okay, we can see that the value of I has been modified, but now it's only one value, and we can say that for sure because dependencies are sound indeed. Okay, and yeah, we basically just negate the guard, and that's it. So this is basically the solution that we provide to the approximation. Okay, and this is so like basically the two theorems that we have in the paper. So basically, okay, sorry, but the Soundness theorem is the one that allows us to know that our semantics are sound. So basically, as I said before, we want to know that we're sound. So when we do over approximations, we want to have all the actual semantics of the program inside our abstract semantics, and this has been proven. I don't want to go into detail for what it says, but okay, trust me. And then the other theorem is a bit more maybe interesting, because basically it's, we call it refutation up to a bound or completeness up to a bound. So the theorem is stating that the semantics are complete up to a bound, meaning that when we enroll loops, we enroll up to some certain bound. And then whenever we have a symbolic state that we know that has a precision flag, basically telling us that we didn't over-approximate, we know that this this symbolic state is going to fit perfectly, and there's no over-approximation, it's complete up to the bound. And then any trace that the SMT generates based on this state is going to be actually allowing us to refute non-interference. And basically, just to have a small image, basically saying, okay, if we have this symbolic state, we can apply some concretization function, and we get a set of pairs of memories that are actual refutation traces for non-interference. So wrapping up, basically, on the paper, we presented this table, which is basically a good way of showing that basically these analyses that I've been showing you are somehow incrementally good, so incrementally more precise. And as I said before, I skipped what we call here RedSoundRSE, so don't mind it too much. But the idea is you can see that we begin by having in the first column dependencies, and we can only prove one program. In the second row, we have the SoundRSE, so it's the relations of execution with the bad over approximation, and we can only prove one. And then, basically, by going to the right, we end up using dependencies and getting a higher precision. And on the bottom, basically, you can see that we also have some examples where we can use this refutation up to a bound, where we have an over approximation, and then we can give a actual refutation trace. Okay, and then, as I said before, basically, we build up all the way to RedSoundRSE, which is our contribution. And I skipped, sadly, RedSoundRSE, but the idea is kind of the similar of dependencies, but instead of using it for a relational symbol execution, we have a non-relational symbol execution, and we can use intervals and polyhedra to have a better approximation of the values. And And basically, the last thing is that we have an artifact we've submitted to VMCAI. But the idea is that you can also mix all the semantics in a very nice way. So you can use the normal sound symbol execution to the symbol execution with the dependencies, or you can also use, if you want, the non-relational symbol execution with intervals, but on the relational symbol execution without dependencies. And yeah, if you try the artifact, you can do this. So that's it. Thank you.
Thank you. Interesting talk. I wondered, you didn't mention too much about the artifact or evaluations. And I wonder about, there's a variety of other tools that can do sound verification of non-interference based on product program, self-composition, property-directed self-composition. Did you compare, if you just focus on the soundness part, did you compare against those kinds of tools?
So, we were actually doing self-composition. But then we didn't really compare to other tools because of first the language we're using for this prototype for the semantics, a simple while language, so we don't have, for example, pointers or anything that is so interesting. And then, well, and also the implementation is very, well, I did it by myself, so it's not like I can compare, for example, time against other tools. But yeah, basically, sorry, maybe I'm missing something from the question, I don't remember.
Yeah, no, because there are other tools that, at least for the examples you gave, that that work on simple while programs without.
Okay, yeah. So I can compare, like I have here, sorry, it's not working. Okay. So I do have some, there are some tools that we looked into, basically to compare. So for example, I think the most similar one is the last one we put here, relational execution, that is by Farina. And the thing here, for example, they're also doing relational execution, they're also sound, but the way they use abstract interpretation is very different because we're using it basically on demand. So we're executing symbolically, and then we hook up dependencies when needed. So in that way, it's different. Well, and they have basically loop invariants that are processed before, and then they add the loop invariants in the symbolic execution. And then there are some other people like, because for example, the first one, leveraging abstract interpretation. So, okay, in this one, basically, they're also doing abstract interpretation with symbolic execution, but it's only dynamic symbolic execution when we're doing static analysis. So for like specifically non-interference, I think the only word that we can apply is like basically the last one by Farina from what we saw. And in that case, yeah, I mean, I think also, like I said before, like the comparison is more like the way we do it, not the precision, the speed or of the language itself. I don't know, sorry.
Yeah, I mean, it could be that the particular strategy that you're using allows you to verify programs that those other tools can't verify. I think it'd be an interesting comparison.
Yeah. Well, I think that the fact is that all the tools that we compared to, they were used in different languages, and they didn't have time to make the language more complicated to match. I think because I don't remember exactly now what this last paper is using, but I'm pretty sure that they had something like arrays maybe or pointers that we're using. So yeah, sorry, but
Okay, thank you.
thank you.
So maybe you could just give a little more intuition about the benchmarks that you tried
Yeah.
with the figures.
Yeah.
Yeah.
Okay. So maybe wait. Oh yeah, because the lag in the mouse is pretty bad. Okay, but basically the idea is that all these programs that we have is programs that we made ourselves. Basically, knowing the limitations and then trying to see, okay, what kind of limitations we can find in each of these different analyses, and then how this combination can be gradually better to prove non-interference. And basically, well, the detail also is that, as I said before, you can combine the relational symbolic execution with the different non-relational symbolic executions. So basically, you can see there the sub-columns basically saying, yeah.
Sorry, my
Yeah.
question was rather about what syntactic features you have in these programs because you cannot get figure number.
Yeah, sorry. No, but so basically, you're asking about the language that we're using.
I mean, you have can have some while loops with the conditionals inside.
Yeah, so-
multiple loops, nested loops.
Yeah, so I don't think any of the programs have nested loops, but then, for example, we have loops and ifs that no arrays, no pointers, and the idea is the different combination of them. For example, what happens if you have a loop and then you have an if statement, and then inside the if statement in the else branch you have loops there. They're actually similar. But then, because you're actually splitting on the control on the if, you cannot use, for example, dependencies, because you're actually splitting the control of the execution. So there's kind of like this kind of problems where it's useful to have intervals in polyhedra.
So what's the difference between the refutation model and the alarm? I mean, if you look at
Okay.
the last one, it
Yeah.
you know, at the bottom
So-
you say alarm. Is it undecided? But obviously you know the ground truths, right? So yeah.
Right.
You
So
created
the thing
this-
is that, of course, like in these programs, we know whether they are non-interferent or not. But then for the ones that we put refutation model, basically, what it means is that the tool was able to not do any over approximation, and then we are able to ask this SMT solver whether the program is non-interferent, and it says, okay, no, it's not non-interferent, and this is an actual refutation trace, so like actual pair of value of memories that is showing us this violation.
And so
other
for the
ones-
last one, you were not able to find it.
Right.
To kind of
Because there are some programs basically where it doesn't matter how many times you enroll the loop, you will basically end up always having to over approximate. So the tool is giving us the correct answer, saying yeah, it's not non-interferent, but we don't know exactly why.
All right, so it's 12:33 already, but we have to send the speaker again and move the offline discussion.